We were counting arrangements, counting ways to select and in some senses sort things. But what if I think about subsets, subcollections? I want a board for a club. There are 10 members. I want 4 people. Assuming no one can wear 2 hats. When we were talking about counting, we were talking about counting arrangements. And we looked at ways in which arrangements could be thought of as different or as equivalent. So let me put a name to this. A permutation of a set is a rearrangement of the elements of that set. By the way, this includes the arrangement they're currently in. Now, we usually think of sets as unordered. So another way to think of this is as an ordering of a set. If I don't do the whole set, but only some number r, where r is less than or equal to n, the number of elements in the set, then I can talk about an r permutation. And an r permutation is an arrangement of r elements from our set. So what I'm asking for in my question about the club is I'm asking for a 4 permutation because I want 4 distinct elements. A 4 permutation from the students in this class, right? Pick 4 of you, stand you up here at the front of the desk in an order, right? So I should be able to count this using nothing more than the multiplication principle. How do I answer this question about my club officers?
Would be like just 10 times 9 times 2 times 7.
Because I have 4 club officers, right? And I don't care what order you put those offices in, president, vice president, secretary, treasurer. I've got 10 choices for that first spot, 9 choices for the second because I've already used somebody, and they're not allowed to repeat entries. Nobody can wear 2 hats. Nobody can have more than 1 position. So anybody who's in this spot can never be used again. Anybody who's in this spot, lost 1 person, they can never be used again, right? But there's another way to think about this. I could think about lining up all 10 people. How many ways can you line up 10 people? Our exclamation point, the factorial. Because that's 10 times 9 times 8 times 7 times 6 to 4, 3, 2, 1, all the way down, right? But I only care about the first 4. So does the order of the last 6 matter? Here are the first 4 people. Here are the last 6. Does that order matter? So any rearrangement of them would be equivalent, wouldn't it? What do I do with equivalent arrangements? Last Wednesday. I could, but I think making a tree diagram might take a lot of work since I'm doing it for 6 choices. What do I do just to count the number of things? What?
Or exclamation mark at the bottom.
Okay. Let's be specific here. I didn't go over that yet, and that's not what this one is, unfortunately. But that is a formula I'm going to get to. It's just not the one that's going to give me this one. If I have a number of equivalent ways, we did the people sitting around the round table, right? And we showed that there were 6 possible layouts, but 3 of them matched and another 3 matched. So we did what? You were here when I wrote this. I didn't hallucinate you into existence last week. We had 6 different arrangements, and we showed that there were sets of 3 that were equivalent. What did we do with the 6 and 3 to come up with how many distinct possibilities there were? I divided. I'm going to take all of the possibilities of rearranging these 6 people on the end and divide by that. So now I have to ask, how many ways are there to arrange 6 people? 6 factorial. So I'm going to end up with this. Now here's the best part. 10 factorial is 10 times 9 times 8 7, 6, 5, 4, 3, 2, 1. Notice I'm multiplying all the way through here, right? And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. If I asked you to write out this fraction and simplify it, what would you do? Instead of multiplying it out, because the 6, 5, 4, 3, 2, and 1, they're all going to cancel, aren't they? And doesn't that give me exactly the same answer as this one up here? This is a better way, or at least in my opinion, a more efficient way to count our permutations. I have the 10 people on top. That's the size of the whole group. And on the bottom, I have the people I don't care about their order. Out of N, we're going to pick R of them. Sometimes you'll see this written as PNR, a permutation from N things, get R of them. Thus the R permutation part. And now I can say this is N factorial over N minus R factorial. I think of this as picking them one at a time. That's how I remember that this is a P. I'm going to pick the first person, then I'm going to pick the second person, and I have fewer and fewer people to pick from every time. So this formula matches the idea of writing out the spots. The problem is that last thing is N minus R plus 1. In our example, that's the 10 minus 4, that's 6, plus 1. My last spot was a 7, wasn't it? Because this first one is N minus 0. So I have a 0 spot, a first spot, a second spot. Oh, that's why I get one more number than what I'm thinking. So there's something particularly important to this counting method. And that's the idea that the order matters. The person who is vice president, if I put them in the secretary spot instead, I'd get a different ordering, wouldn't I? Order is important here. I chose this person first, this person second, this person third. If I wanted 3 of you to give first, second, and third prize to, order would matter, wouldn't it? You'd be happier to win first prize than third prize, probably. So in all of these calculations, it is important to remember that the order matters. And that no one can be chosen twice. Another way to say that idea is that I know all of these elements in my set are distinct. Right now, there are 12 of you in this room. I want 3 of you. How many ways can I do it? In order. First, a second, and a third. Right, because what I'm doing is this calculation. Now you could do it like that by writing out the multiplications for 3 spots. And then 12 times 11 times 10. 12 times 11 is 132. So this is 1,320. Questions? Seems straightforward at the moment? I promise it gets weirder. But I like this. This is simply a compact way of writing out my multiplication formula. I have to be careful though. If I have a group of 5 and I want to line all 5 of them up, out of 5, pick 5. Order matters. What happens when you do this calculation? Using our formula. Careful. I don't actually get 0. I get 0 factorial. Yeah, that's a weird idea. If that's 0, then I'm screwed, right? I'm dividing by 0, and my calculator goes. So 0 factorial can't be 0 for this to work. I am going to put in front of you right now, on the screen, a complete ordering of all of my Olympic gold medals. Ta-da! I don't have any, but I can put them in an order. That order is an empty set, isn't it? That's an ordering, isn't it? Hey, here they are. One way to do this, an empty set. So the best way to make this definition work is for 0 factorial to be equal to 1. That would match my other version of the definition, wouldn't it? 5 times 4 times 3 times 2 times 1 is 120. And that's the top of that fraction. But that's also 120 divided by 1. That works. You sneaky mother. I cannot tell you the number of times they say, well, that's 0. Ooh, but it's actually 0 factorial, and that makes it something different here. Questions? Okay, monkey wrench time. The factorial function is only defined for whole numbers. I'm ordering 5 things. I'm ordering 7 things. I'm ordering 12 things. That's a function that's really very limited in its domain. It would be nice if we could get a larger domain. If that's true, then there should be a way to define 1/2 factorial. That is an absolutely insane sounding idea. But there are several different methods by which I can take the factorial function and make it bigger and make its domain move from just natural numbers to real numbers. The idea is called analytic continuation. And when we do that, we get a function called the gamma function. That is a capital letter gamma. Sometimes it has a little foot on it, and it kind of looks like you're playing hangman. The gamma function has the property that when you feed it a natural number, you get the factorial. But gamma itself has as its domain the complex numbers. And it works. You can now define negative factorials and fractional factorials by defining them as gamma of. That's freaking weird. And that's as far as I'm going on that. But if you want to learn some really neat ideas, this idea of analytic continuation gets talked about in complex variables. That's really where it lives, is in the complex plane. And between myself and Dr. McNabb, that's one of our favorite courses. Both of our research areas are in complex numbers. So if you're interested in this even tangentially, and you're like, that's bizarre, this is related to another one of those Clay Millennium Prize problems. The idea of analytic continuation is part of the Riemann hypothesis. Okay, that's as far as I'm going to go with that. I'm going to take photos at a wedding. I have the bride and the groom and two groomsmen and two bridesmaids. How many ways can I line up these people to take pictures? There are 6 people up there, right? If I just want to put them in an order and take a picture, that's 6 factorial ways. Yes? But that means that a legitimate ordering for the picture is the bride, the 2 bridesmaids, the 2 groomsmen, and the groom. Does that make sense? That's really kind of dumb, isn't it? It's a wedding picture. Don't you want the married couple next to each other? So how can I adjust my counting idea? I'm going to put together ideas from last week and this idea today. How can I rearrange my counting idea? Keep the bride and groom together. Let's put them in a sack. That'll be fun, right? Bride and groom, kidnap them, off they go. Consider them one unit. And then instead of having 6 people, I really have 5 units. And one of them is the combined bride and groom. So then I get the bride and the groom, bridesmaid 1, bridesmaid 2, groomsman 1, groomsman 2. And I can think of these 5 objects. How many ways are there to order 5 objects? But we wrote down that number, that's 120, right? But I order these 5 objects. And now I have, say, a bridesmaid, a groomsman, the sack, a bridesmaid, a groomsman. And then I open the bag. There's an option, isn't there? There's an or here. What's the or? Or order. Is it bridegroom with the bride on the left, or is it bridegroom with the groom on the left? That's going to matter, isn't it? That's going to give me 2 different orderings. So really, whenever I see an or, what does my formula from last week tell me to do? If there are n1 ways to do task 1, and n2 ways to do task 2, and nk ways to do task k, and I get to do one or the, what do I do with or? I add them. So when it's bride-groom, there's 120. When it's groom-bride, there's 120. And I add because those are exclusive. There are actually 240 options. So when the order matters, I need to take into account how I am treating the items in my list, whether any of them are subcategories and other sets within there. I might need some of my other formulas. Questions?
I'm gonna say, it says 2 tens on each side, so we just gotta change.
You're right, and I apologize for using that phrase. I meant on each side of the bridal party. 2 attendants for the groom and 2 attendants for the bride. Not they have to be on 2 on each side of the picture. Well, because if that's true, then, I have much fewer options, don't I? And that becomes a whole different counting strategy. If I know it's going to be 2, 2, and 2, then I'm really ordering just those 2s. 2 options for the bridesmaids, then the bride, the groom, the groomsman, and then that whole thing flipped. What if I don't care about the order? I was picking a group of 3 out of this room, right? Okay. And I said there's going to be a first and a second and a third place. Well, what if you're all getting the same thing? And it doesn't matter. You all 3 get a $10 Starbucks card here. Does it matter who came up first, who came up second, who came up third? That means that I have some more equivalent ideas, don't I? I'm going to pick on the front row. Jolanta, Dean, Chris, you 3. But does it matter which order you come up here and stand up here in? How many ways are there to order the 3 of you? 3 factorial is 6. What do I do with that number 6? Those are equivalent methods. What did we do with equivalent things? We divided. So, I'm going to divide again. That means my number should get smaller. My number should get smaller. I can take out of R things I'm sorry, are things chosen from n things. When the order mattered, we did NPR, right? But now I don't care about the order of the R things. So I'm going to divide this by R factorial. I chose 3 of you, so I'm going to divide by 3 factorial. If I choose 6 people, I'm going to divide by 6 factorial. I'm going to divide by however many ways there are to arrange that group. Wait a minute. Here's this formula. This is n factorial over n minus r factorial. And now I'm dividing by another r factorial. Take this out of the bottom and flip it over. It goes on the bottom. We were choosing from the 10 people in our club. We were choosing 4 of them to be officers, right? And I could say, I just need to know who the officers are. You sort out which one of you is going to be which. I just need 4 names. Then I don't care about the order. I just need the names. Well, then I'm going to do that. And now I'm dividing by 2 things instead of 1. So I need to remember to put those in parentheses on the bottom. This is 10 factorial over 6 factorial. That was the same as before, but now there's another 4 factorial on the bottom. If I do all of the canceling, I'd get 10, 9, 8, 7 on the top, right? But that would only cancel this part. I'd still have 4, 3, 2, 1 on the bottom. And that's a smaller number. What is that number? $210. Which is a lot bigger than just the 10 times 9 times 8 times 7. Sorry, a lot smaller than just 10 times 9 times 8 times 7. If I'd just done the permutation, then the order would matter and I'd have a lot more ways, yes? Okay. I need a new name for this. If those were permutations because they were order matters, I'm going to call this a combination. I'm going to use C, and I'm going to call this NCR. Sometimes it's also written CNR, and sometimes you'll see it written almost like it's a fraction, but there's no bar in the middle. It's just got a set of parentheses around it. This is referred to as a binomial coefficient. I remember this as an unordered selection. So when I was doing a permutation, I was picking them out one at a time. And I see my fingers coming in, pick them out one at a time. And this helps me. Anybody speak ASL? Okay, get on the internet. What's the sign for the letter P? A, B, C, D, E. Fingers are pointed downwards. Picking them out one at a time. On the other hand, if I don't care about the order, I can just scoop them all up. It's the letter C. My hand helps me remember this. An unordered selection, but still a finite one with no repetition allowed. If I am choosing from multiple groups, then I can go back to last week. I can say, how many ways are there to get a team with 3 boys and 3 girls from a group of 9 boys and 5 girls? If I don't care about the order at all, well, then I can think of this as really choosing 2 separate piles. Out of the 9 boys, I'm going to choose 3 of them. And out of the 5 girls, I'm going to choose 3 of them, right? Out of the 9 boys, I'm going to choose 3 of them. And out of the 5 girls, I'm going to choose 3 of them. What do I do when I hear the word and? Or was addition, and is multiplication. So the correct way of counting this is to say I'm going to do 9C3 times 5C3. I have no idea what these numbers are, but I'm going to cheat. Where's your factorial button? If I want to do 9C3, I'm going to need 9 factorial at some point. I don't have that number memorized. Where do I find the factorial button?
Math, and then the 1 is 3.
That's probability. Right above the factorial button are permutation and combination formulas built into the blessed calculator. You want 9C3? I already typed the 9, right? I was going to do 9 factorial. I can just tell it, hey, do NCR, and that second one's 3. That's 9 times 8 times 7 divided by 3 times 2 times 1. Boy, that saved me a lot of work, didn't it? It's particularly useful when my groups are a lot larger than this. I mean, 9, 8, 7, those are numbers that are reasonable, right? Let's pick a set of objects that is a lot of objects. A deck of 52 cards. Anybody play poker? At least a couple of hands going up. You get 5 cards in poker. How many possible poker hands are there? I hope it's a lot more than that. I get 5 cards, right? Does it matter what order I get them in? Because I get to rearrange them however I want. How many cards are in the whole deck? 52 of them, and I get 5 of them. They can't be repeated because if the deck has 2 aces of clubs, somebody's getting shot. Or you're playing with a lot of decks of cards, which is a whole different counting game. Repeatable objects are not in these formulas. I'll save those. That's a huge number. 2,598,059 960. 2.6 million different poker hands. If you play cards, if you play poker in specific, that should be a number you never forget. Because all of the things you want to think about are based around that many options. So now you start asking, how many ways can I get a certain hand? Best possible hand in a poker game? Dean, you said you played? What's the best possible hand?
Royal flush.
Royal flush. A royal flush consists of a 10, jack, queen, king, and ace that all have the same suit. How many ways are there to do that? And no more. There are exactly 4 ways. These 5 cards in hearts, clubs, spades, diamonds, that's it. The least valuable hand, other than nothing, is 1 pair. So here's a question of, I'm going to write over here, 4 ways. How many ways are there to get a pair? And nothing better. I need to know a little more about a deck of cards, right? There are 13 different values. The jack, the queen, the king, and then ace through 10 as spotted cards. So that's the number of pips on them. So I have 13 different values available. One of those I'm going to get a pair of. Might get a pair of jacks, I might get a pair of threes, I don't know, but I'm going to get a pair. So I need a value out of 13. Pick a value. Now, I don't care what order you pick that value in, but you're only picking one thing. So that's really just 13. But that 13, that value has 4 cards. How many of them do I get? I get 2 of them. So now, out of those 4 cards, choose 2. That's the word and. Pick a value and take 2 that match that value from the 4. What about my other 3 cards? They don't match, but they do matter. They can't match this value, and they can't match each other, right? So out of the 12 remaining values, they all have to be different. Out of the 12 remaining values, I need 3 different ones. Now, each of those values have 4 cards. How many of those value cards can I get? For each of those values. I can only get 1. So I'm going to take 4, choose 1, and I'm going to do that 3 times. Now, if this is making you a little crazy, you could think of in your hand, you picked your pair and put them at the left two cards. There were 13 options for the value here, and out of the 4 cards, you got 2 of them for C2. Then here, there were 12 options, and you got 4C1 of them. And here there were 11 options, because you can't use either of these values. And you got 4C1. And here there were 10 options, and you got 4C1. But it doesn't matter what order those appear in, does it? So I need to divide by 3 factorial. Because there are 3 items here, and I put them in any order I want. Well, 12 times 11 times 10 over 3 times 2 times 1, that's 12C3. That's where I got that from. This is a large number of ways that this could happen. What does this turn out to be? Ooh, big, way bigger than that. I meant this whole thing. Yes, this should be 220, I think. C1 is 13. 4C2 is 6. 12C3 is 220. 4C1 is 4, but that's cubed. How many options?
It's 1,098,200.
There were only 2.5 million hands in the first place, right? 1 million plus are 1 pair. That's why this is the least valuable hand. It's fairly common. And that's why a royal flush is so valuable. It's so uncommon. In my entire life playing poker, I have exactly 1 royal flush to my name. 1. And I was playing online back in the 1990s. For $0, man. I don't gamble like that. But that brings me to the next question. How likely or unlikely is an event is really a counting strategy. And so quantifying likelihood is really counting. Now, that's the end of the material I'm going to look at in chapter 6. Repeated objects, multiple copies of objects, expansions on this. There's a lovely discussion of Pascal's triangle and how it's related to all of this idea as well. Is the rest of chapter 6. We're going to save most of that for the Prob and Stats course. But it does mean all of chapter 4, all of chapter 5, all of chapter, this is a good place to stop. That means we're going to have an exam a week from today. The review sheet is posted. You will get another formula sheet. Just like the last one. No worked out examples. I will see you all on Wednesday. Have a wonderful day.